All right, we're going to talk a little bit about what distributed consensus is, but before we get to distributed consensus, I want to point out how it's used. I mean, it is the underlying technology behind things like Bitcoin and Ethereum having the ability to resolve a transaction across all these nodes into a single result. Okay? Now, there are different methods for getting distributed consensus. There are 3 of them that I know of. And the first one of those is what we see in Bitcoin. And that is the Byzantine generals problem, Byzantine fault tolerance. There is the method that we see in more second generation. And that is things like Cardano's proof system. This is the Ouroboros protocol. And both of these have lots in common. They are basically very similar. So I'm going to call that's method 1. The second method that you use for getting distributed consensus is really what we see in the F1 database from Google, which is a time-based protocol. And the third method is the Honey Badger Byzantine fault tolerance solution, which is a cryptographic solution. So we're going to talk a little bit about this one. I don't know if we'll actually cover anything on this one in this class. You can search for it. It's based on doing distributed threshold computations on encrypted data. So you're actually communicating it, or you're actually doing computations, homophoric calculations on the encrypted data itself. This is the stuff that I worked with at Thesis a few years back, and they have it up and going. There's a group at Berkeley that is using this to build basically a third generation blockchain. We are going to talk a little bit about F1. And F1 is the database at Google that they built to solve a particular set of problems. The particular set of problems is they went through their code and they determined that in non-SQL databases there were 2 kinds of errors. There was network errors. This was about 90% of their defects. And there was concurrency errors. And the concurrency errors were there because most non-SQL databases, including some things that they were doing, MongoDB, for example, don't have ACID compliance, and consequently they have eventual consistency, but that eventual consistency requires that the application actually build the consistency into it. And building this ACID compliance, which is what you see in SQL, took decades of hard work, with a lot of people grousing over the details of how to get that stuff to work. Literally decades. So this stuff was really hard, and when you put it inside applications, it generally was not right. And it produced all sorts of very expensive, very hard to fix errors. So Google's solution was they went back to look for a distributed consensus mechanism that they could actually build a SQL database on top of. And they took both MySQL as a front end, and they took Postgres, and they built those on top of a consistent block store called Bigtable. And to get this to be consistent with SQL, they used a couple technologies, including being able to use atomic clocks in their data centers and a protocol called Praxios to be able to make this consistent. Now, when we look at the distributed consensus mechanism out here in blockchain, Bitcoin takes 6 minutes, plus you need about 10 transactions, so about an hour. Ouroboros does this in about 10 seconds. Ethereum is about 22 plus 4 or 5 transactions, so about a minute. So that's what you get when You don't trust anyone, and you're building this distributed consensus, but you're building it across a network with no central nodes. Google, with their atomic clocks, does the same thing in a millisecond. But, those atomic clocks didn't come cheap, and they have control of the network so they can get a reliable network, and to the point where Google put their own transatlantic cable in this year so that they have better network control. So they've got some investment over here. Don't underestimate the difficulty. Now, you can use this same system over here with a database called CockroachDB that is open source, and you can set it up. I have. It works pretty good, but again, with CockroachDB, you're looking at more like 3 to 7 seconds at best. And realistically, most people are looking at about 30 seconds to get consistency. So what is this distributed consistency problem? And, over here in the blockchain world, we've got the benefit of no central node. It's reliable, it's fault tolerant, it can stand outages of nodes and keep working. There's a lot of advantages. But at the same time, over here in the blockchain world, we have things like Bitcoin, and it has no central node. That's one of its big disadvantages, and I'd like to explain why that's a disadvantage. The biggest thing for a disadvantage for that is that blockchain as a currency doesn't have something like the FTC. There's no central authority setting the value or manipulating the value. And you go, well, that's good. They shouldn't. Maybe. Now, there's examples certainly of not just FTC, the Fed. Okay, that might be a better central controller, the FED, the Federal Reserve. Not the Federal Trade Commission, the Federal Reserve. Setting the central value. Now, there are plenty of examples of a central bank doing really nasty things to currency, like Argentina in the 1970s. And Venezuela these days, right now, okay, where we see, 1,000,000% inflation. Okay? Their currency is basically worthless, destroying the value of a currency. Now, with no central authority, you're not going to see that in Bitcoin. If the value of Bitcoin falls, it's either because there's something wrong with the network or because we get mad at the amount of electricity that it's using because it's an environmental disaster and we ban it. But that doesn't mean that these other protocols out here like Ouroboros are going to be affected. They don't work the same way. They work the same way for this piece, but they're not using proof of work. So they're not burning up electricity like it's going out of style. But if you look at the track record of the Fed, if we drew a graph out here over time, starting when we have data about 1870, up through, I'll put in 1930, up to 2020. And we drew a graph of soybean prices, stock prices, the value of the dollar. What you're going to see is that if I have a 0 point here, rate of growth of the economy, the reason I put 1930 in here is because this is the Great Depression, and it's also the beginning of the Fed. And you can look at a bunch of these graphs. I've put one in the inflation log graph in the notes. And on all of these, what you're going to see is you're going to see a graph that looks like this. Okay. Most of them, for a lot of them, you get the Fed, and you see some things like this afterwards. And it's really apparent on a lot of these that suddenly, they put in the Fed, and the Fed started doing a good job. There are some of them that you'll see some spikes like this for World War II and the Great Depression, or the other way, depending on which graph it is. But by about 1950, okay, it's been pretty darn stable all along after that. And, before it was ugly. So I would say the Fed, by and large, has done a pretty darn good job at smoothing out the economy, making recessions less severe, depressions less severe, keeping prices from skyrocketing up and down, and Bitcoin doesn't have something like that. It doesn't have a central authority. So you should expect this kind of behavior. That would be my thing. Now, the good thing about that is we don't have these kind of behaviors with 1,000,000% inflation because they're trying to do nasty things to the currency. The bad thing is, yeah, it's going to have some volatility. Most definitely it's going to have some volatility. So let's talk about the Byzantine generals problem and Byzantine fault tolerance. The first part of that is the generals.